On Earth, we move between points that are fixed between each other, like going to your friend's house or to the shops. These objects don't move. But in our solar system, all bodies are in continuous motion. Man has long observed the movements of the sun, the moon, and the stars, measured angles, distances, gravitational strengths, and orbits, only limited by the technology that is available to him. The sharper tools of the 20th century have allowed man to notice how the sun and other planets move with relation to other stars in the galaxy. Then, man leaves Earth, April 12th, 1961, with a journey into space, and this is where we pick up. Once in space, man's spacecraft will navigate him with instruments and modern science techniques inconceivable to how one would navigate Earth. No tom-toms here. There are two aspects to how a spacecraft would navigate in space. One, knowledge and prediction of the spacecraft's position and velocity, aka orbit determination. And two, knowing when to fire the rocket motor to alter the velocity, aka flight path control. Even though the spacecraft will be travelling at tens of thousands of miles per hour, it will seem to the men on board that they just hang motionless. There will be no day or night. Where they left Earth is now only a point in space. Say man was on his way to a distant planet. His spacecraft is actually in orbit around the sun, as is the planets, or their destinations. That is also in orbit around the sun. They will not be moving directly towards the planet, but instead on a curved path to a different point in space past the sun where they hope to intercept. Say, in this example, they were going to Mars. An error in velocity of less than 1/10 of 1%, which is around 25 miles per hour in this case, would mean that they miss Mars by 300,000 miles. That wouldn't be very good. However, error in space travel may be corrected in flight, because the principles of space navigation are based on the knowledge that the forces involved are constant and predictable. In our solar system, each planet is locked in orbit around the sun, based on its particular velocity. The planet's momentum, this way, along with the force of the sun's gravity, equal out to make this curved path. Oh, that's not very curved. The inner planets, where the pull is greatest, travel faster than those further away, where the pull is weaker. If a spacecraft is to leave the Earth for another planet, it must increase or decrease the speed imparted to it by orbiting the Earth. Either way, this velocity is a fraction of the orbital speed of the Earth, which is 66,000 miles per hour. The velocity imparted by the Earth puts the aircraft into the ecliptic plane of the Earth's orbit around the sun. It would take a lot of energy to come out of it. All planets have their own ecliptic plane. Each one goes the same way, and in this galaxy, those planes go around the sun. Unlike a planet, a spacecraft may change its orbit and its direction because it can change its velocity. When a spacecraft escapes the Earth's gravity in the same direction as the Earth, as in this way, its greater momentum around the sun overbalances the sun's pull, throwing the spacecraft outwards. Then, as the aircraft begins to slow, the sun's pull gradually pulls it inwards. It would then speed up, then the momentum would throw it back out again. Equally, if the aircraft was to come out of the other side of the Earth, then it would fall immediately inwards, gaining speed as it reached the sun. Then, unless it could slow down, it would be thrown out and have a curved path around the sun, and then As it slowed down, it would be pulled inwards and speed up again. Obviously not that close or they'd fry to death. It is the controlled velocity change which changes the course of an orbiting body. The course of a spacecraft can never be completely accurate because even the most advanced pieces of equipment can't account for the tiny errors when taking off. For a spacecraft to know where it is in space, we use this piece of equipment called a sextant. The astronaut will use angles. It will measure the angle between a nose star and a planet. The pilot will record this angle and the exact time he or she sees it. This angle defines a cone of position, as the angle between the planet and the star could have been sighted from any surface of that cone, but not one sighting will tell it. So this is the angle, and there is a cone. Try to make this as 3D as possible. And anywhere within this cone is where the rocket could be. However, the pilot does know that he is close to his trajectory. Knowing his speed, elapsed time, and possible percentage error will put him in a football-sized field volume of possibilities called the estimated ellipsoid of position. The place where it intersects the cone allows the pilot to have a better idea where he may be. Redraw the cone. Thank you very much for watching.